So now let's start to introduce the character group, or sometimes also called the dual group. Okay, so character dual group, they're essentially the same thing. Starting from here, let's let G to be locally compact and abelian. So let's use LCA. Okay, so this is essentially locally compact Hausdorff and plus the condition that is abelian. Okay, so I'll use LCA as abelian locally compact Hausdorff. All right, so the character group, it has a nice definition, so let's define it. Okay, so a continuous homomorphism, so let's say phi from this group G to the unit circle. Okay, this is called a character of G. Okay, it's called a character. So here's the name of G. So essentially, all the character forms the character group or the dual group. Okay, so the set of all the continuous homomorphism or all the characters is called the dual group. And let's use the notation. Okay, so let's denote it by the G hat. Okay, so this is our notation. And so first of all, this I really need a continuity. You can convince yourself why. Okay, so without a continuity, this even if your G is just the real line, without the continuity, your phi can map a bunch of random things to very random places. So it's very difficult to study how they are going to integrate. Okay, so eventually I want to integrate these characters. Okay, so that's why we do need the continuity here. And the second thing is that this G hat turns out to also have a group structure. Okay, so let's look at observe. I have this G hat has a group structure. So where is the group structure? Well, it's essentially just a bunch of functions, and you can do it. You can multiply using the pointwise multiplication. Okay, so first of all, you have a identity. Sometimes you use the say phi 1 to be the map where it maps everything into 1. Okay, so phi 1 is the identity. Okay, and the multiplication is given by the pointwise multiplication. So if you have, let's say, phi, probably shouldn't use phi 1 here. Maybe let's use phi e, okay, as the identity. So if I have a 1, phi 1, and then I multiply a phi 2, if I want to evaluate G, you just do the pointwise multiplication. So phi 1, phi 2 of G. And you can convince yourself, because everything here is abelian, it's quite simple to see that this is well defined and it's also a character, okay? And finally, the inverse is given by basically the conjugate, okay? So if you want to have a phi 1 of G, okay, I don't need a 1 here. So if phi of G times the psi of G is always equal to 1, then you can see that the psi of G is essentially just phi G, the entire thing inverse. But phi being a homomorphism is equals to the phi of G inverse. Okay, so that's one way of thinking that. And another way of thinking that is that this phi G inverse, because phi G is inside the unit circle, so this is inside the unit circle. So the inverse of that is essentially just its conjugate. Okay, so you can also say this is just conjugate phi of G. Okay, and clearly, if phi is a character, its conjugate is also a character. Okay, so the conjugate is inverse. Okay, so this is phi inverse of G. Okay, all right. So basically, now we have a group structure on this G hat. Okay, so if you want to do some sanity check on some simple examples, so the idea is that this phi, when G is the unit circle, this phi looks like this e to the in theta. Okay, so those are the kind of the homomorphism from the unit circle to itself. Okay, and if you recall these phi in the classical harmonic analysis, well, is basically when you do define the Fourier transform, you integrate against these characters. Okay, so that's kind of your analog of these Fourier transform. Okay, so we'll talk about these Fourier transform later. But the main thing I want to show is the following. So here is a lemma. Okay. So I want to show that first of all, each of these phi is going to give you some linear functional. It corresponds to some linear functional. So let's do the following. So if I have phi inside this G hat, okay, so it's in the dual group, then I can define, as I'll actually call this Fourier transform later, but let's just use the notation here for now. So I define phi hat, okay, I take a L1 function f, okay, that's going to return the integral of this f of x and integrate against phi x bar dx. So let's just use the dx as the integrate against the left higher measure, okay? All right, so this is sometimes also called a Fourier transform. I'm going to leave it later, so I'm just call it Fourier transform now, okay? All right, so this phi hat, it turns out to be a map. Well, first of all, it takes an L1 function. It's clearly this integral is well defined on the L1, okay? You can convince yourself why this integral is defined as long as f is in L1. But the idea is that this phi hat is going to define a maximal ideal space inside the L1 of G. Okay, so the claim is that this phi hat is inside the maximal ideal of L1 of G. Okay, in other words, this phi hat is linear, continuous, and is going to be a multiplicative linear function. Okay. All right, so let's give a proof. Okay, so this phi is linear. That's pretty clear. I'm not going to prove that. Is also going to be continuous because if you consider phi hat f the norm, okay, it's going to be less than or equal to the integral of the absolute value. So let's write everything down here. And because your phi has norm 1, okay, the phi of x always in the unit circle, so you do the absolute value, it just disappears. Okay, so this is going to be the integral of the absolute value f. Okay, and this is essentially just the one norm. Okay, so phi is indeed linear functional. So let's just write it down here. So it's inside L1 G, the dual space. Okay. So now I want to show is multiplicative, and remember the multiplicative is basically respect to the multiplicative structure on the Banach algebra. Okay, the L1 of G under the usual pointwise multiplication is not a Banach algebra, but the multiplication as a Banach algebra is the convolution. Okay, so always remember that. So when I do phi hat, I need to check that if I convolute two L1 functions, then I get their the product of their phi hat of f and g, I guess. All right. So let's just write everything out. Okay, this is going to be a bunch of integrals. So let's write. First of all, by definition, this is the convolution evaluate at x. You have a phi bar of x dx. Okay, so that's just definition. And let's write out the definition of the function convolution. So you integrate the f of xy inverse g of y, and then you have a dy here. Again, dx, dy are just the usual left higher measure. And then you have a phi bar of x dx, okay? And you do the standard trick, you change the integral, okay? So let's do the integral x first. So let's do the gy outside. And you're integrating f of xy inverse, phi bar x dx, and then you do a dy, okay? So because your group here is abelian, so it doesn't really matter where you put your y inverse on the left or on the right, okay? So let's just pretend the y inverse is on the left, okay? So in general, you can't really do this, but now because everything is abelian, so I can do y inverse x instead, okay? So this is by g is abelian. All right, so now you do the standard trick. Okay, so you kind of replace x by yx and use the left invariance. Okay, so this is going to be integral of g of y, and you have an integral of f. You replaced x by yx, so you have a fx here, but then you have a phi bar of yx. Okay, let's say entire thing bar, and then you have a dx dy. And because phi itself is going to be multiplicative, okay, so you can break it up into gy phi bar of y, and then you integrate fx phi bar of x. Okay, you have a dx dy, and you realize, well, the inner one doesn't really depend on y, so you can move the dy to the other side. So let's just move dy to the other side. Let's say dy here, and for each one of them now it's pretty clear. This is just the phi hat of g times the phi hat of f. Okay, so your phi hat is indeed in the maximal ideal space. All right.